So when we talk about design topics, we get into talking about safety factors and then stresses in bars, how to size the diameters of the bars. But all those kind of problems typically revolve around finding forces in structures first. In other words, we need to do the statics to find the forces or the reactions on the structure in order to do the mechanics of materials. For my students, I give you a list of example structures that I expect you to be able to do the statics for on an exam, and then you'll answer some questions about the stresses in the bars and so forth. So I want to go through those example structures, and show you how to do the statics for those. So this will just be some examples. Now, here's the first one. Here's a 3-bar truss, and these are all pinned on each end, making them all 2-force members. I expect everyone to be able to find the forces in each of those 2-force members and find the reactions at the supports. Now, when I say a structure like this may be on your exam, if I take the structure and I rotate it 90 degrees, or if I put the load going horizontally instead of vertically on the picture, or change it up a little bit, I consider that the same kind of structure. Okay, so if you know how to do the statics for one of these, then if you rotate it 90 degrees, it doesn't change the statics. Now, in order to do an example, I need to put in some numbers, and I would encourage you to put your own numbers in to these kind of problems as well and work it out. You can bring it to me, and I'll take a look over it. So I got one number here. Let's say that from the top to the bottom of the structure is 5 meters. I'm just going to make up a few more numbers. Maybe from the roller to this position where this bar is at is 2 meters. Okay. And then over this way, let's say that's 4 meters. I'm just making up some various numbers right here. And let's put a force on here of maybe 10 kilonewtons. All right, so again, just to find the statics, what I would usually want to do first is draw an overall free body diagram. Now, a free body diagram is where I draw another picture, I get rid of the supports, and I replace those supports with the appropriate reactions. In this case, since I have a pin up at the top, it's a pin connection, let's call that A, I might have a reaction that goes A in the X direction and a reaction in the Y direction. I'll call AY. Down here at the bottom, maybe that's position B. We'll call that point B. I have a roller. You see the little rollers right here. That causes a reaction just perpendicular to the surface on which the roller is resting. That would be in the X direction in this particular problem. Okay, so to find the external reactions, I'm going to do the summation of moments. Let's do the summation of moments about A. Okay, so those two reactions have a zero-length moment arm. I will have, according to my sign convention of this way positive, I'll have the force Bx times 5 meters. And in the negative sense of rotation about point A, I'll have the force of 10 kilonewtons times the offset distance of 4 meters. All right, so I'll solve that for Bx. And in this problem, I have 40 divided by 5. I believe that should be 8 kilonewtons for the reaction at B. If I wanted to find the reactions at A, I can do the summation of forces in the X direction. I will have AX plus BX equal to 0. Since I already know BX is equal to 8, AX is going to be equal to minus 8 kilonewtons. And then the summation of forces in the Y direction, it's pretty straightforward. We have AY minus 10 is equal to 0. AY is equal to 10 kilonewtons. When you do your statics, again, you start with a free body diagram. We just talked about that. But I also strongly recommend that you put in your sign convention for your summation of forces and your summation of moments, so you don't get confused as to which way you're calling the positive direction for the summation or the negative direction. All right, so now we have those reactions, but we may want to find the internal forces in bars 1, 2, and 3. And the reason why we want the internal forces is to calculate the stresses. So the stress in bar number 1 would be the force of bar number 1 divided by the cross-sectional area of bar number 1, and so forth. Okay, now this is where we want to move to the method of joints or the method of pins. Let's take a look at position A. Let's draw the free body diagram of the pin at A. We have AX, which we just found out. I'm going to draw it that way, but its value is -8. It really means it goes the other way. We have AY, we found that to be 10 kilonewtons. And anytime I remove a bar from the structure, I have to replace it with a force. So I have a force that comes down this way, and that'll be my force from bar 2. Then I'll have a force that comes this way, off at the angle that this bar makes. I'm going to call that F1. Now, by drawing these forces coming out of the pin, that is equivalent to assuming that the bar itself is in tension. That may or may not be the correct assumption, but we'll find out in the end if we get a positive number or a negative number for force F1 and F2. And bear with me a moment on that, and we'll point it out. Now, because there's a pin on this point right here and a point right here, nothing in between this bar, that makes this bar F1, bar 1, and bar 2 two force members. Because they are two force members, the line of action of the force goes down the axis of the bar. What that means is that this angle in this picture, I'll call that theta 1, is the same as this angle in this force diagram right here. So we can use a little bit of trigonometry to figure out what that angle is. All right, so to find out what that angle theta 1 is, if we look at this triangle from here to here, we know that's 4 meters, and the remaining distance is 3 meters from A to that spot where we're using this right triangle. So now I have a right triangle. Okay. So I'll write it right here. Tangent of theta 1 is equal to 4 divided by 3. Okay, this is kind of nice. It's a 3, 4, 5 triangle. If we want, we can just use that information, or we can put 4 divided by 3 into our calculator and take the inverse tangent. That ends up being 53.13 degrees. So now when we go to this pin at A, we're going to do our equilibrium equations here. We're going to do the summation of forces in the x direction. We have -8. So even though this arrow is pointed in the right positive direction, the value is -8. So that's why I have it here as -8. And we don't have any component of 10 in the x direction, don't have any component of F2 in the x direction, but we do have a component of F1 in the x direction. It's going to the right, as I've assumed it here, so I'm going to have plus F1, and we need to think about this. Do I need the sine theta component or the cosine theta component? And in this case, I need the sine theta component for theta 1, equal to 0 for equilibrium. Let's talk about why we need the sine theta component. Let's just draw the force F1 right here. By tip to tail, we know these are the components of the vector, and this is the angle theta 1, and this is the hypotenuse. That's the force F1, and this is the adjacent side, and this is the opposite side. The sine of theta 1 is the opposite over the hypotenuse. Okay, but the hypotenuse is F1. So if we solve this for the opposite side, the one that's in the horizontal direction, the x direction, that's equal to F1 sine theta. All right. So once you get used to doing this, it comes pretty naturally, but if it's been a while, you may need to refresh yourself on that. All right, so now I'm going to solve for my force F1. I know that my angle is 53.13 degrees, so I'm going to move the 8 to the other side and divide it by the sine of 53.13 degrees. Okay, let's see what number I get. I get 10. Okay, so that's a nice even number. 10 kilonewtons. Now, if I wanted to find the forces in the x direction, if I want to find force F2 rather, I will do the summation of forces in the y direction. Let's take upward as positive. I have plus 10 minus F2, and then I'll have minus F1 times the cosine of theta 1 equal to 0 for equilibrium. If I want to solve for F2, that's going to be equal to 10 minus 10 cosine 53.13 degrees. And make sure your calculator is in degrees. I'll take the cosine of 53.13, that's 0.6, multiply it by 10, gives me 6, and I'm going to subtract it from 10, that gives me 4. So that tells me that the force F2 is equal to 4 kilonewtons. Now, if I want the force in bar 3, I can either take a look at this pin at B, or maybe this pin right here at C. The easier one, in my opinion, is the force at looking at B, the pin at B. So let's do another equilibrium free body diagram for point B. Now, Bx we found was 8, and it does point in that direction. We have F2, and we have F3 coming off at this angle. Because this is a roller connection, there is no y component on the reaction at B. All right, so now we need the angle that goes this way. Call that theta 3. Okay, so if I look at this picture, that's 4 and that's 2. The tangent of theta 3 is equal to 4 over 2. So this one can take 4, can divide it by 2, and then take the inverse tangent. That's 63.4 degrees. If I do the summation of forces in the x direction on this picture, I'll have plus 8, and then I'm going to have plus F3 sine theta 3 equal to 0. All right, so I'm going to take 8, move it to the other side. I'm going to divide it by the sine of 63.4 degrees. Okay, and I got 8.95, let's call it 8.95, but if you notice, that has to be a negative number, so it's going to be minus 8.95 kilonewtons. Now the negative right here, what that means is the force really goes in the opposite direction. I had assumed that this force goes out this way. Now, if I were to draw the free body diagram of bar number 3, this corresponds to assuming that the free body diagram of bar 3 looks like this. But it's really going the opposite way, since the negative sign on a force changes the direction of the force arrow. So I can draw it like this with minus 8.95 kilonewtons, or bar 3 I can draw like this with a positive 8.95 kilonewtons. The point is, no matter which way we go with it, we need to realize that bar number 3 is in compression. All right, now what else can you do with this problem? If I wanted the stresses, I would take those forces and divide by the respective cross-sectional areas. If I wanted the shearing stress at pin A, I would take the shear force at A divided by the area in shear. Okay. Since I have an X and Y component, the shear force magnitude is the square root of AX squared plus AY squared at A. And depending on what goes on at the pin, I may be in single shear or double shear, but in any case, I would divide that by the area in shear. Now, there's different ways to ask this kind of question on an exam. I can leave the force as a known value, and you can compute the numbers for the stresses, or I can leave the force as an unknown quantity, and I can give you the strength and safety factors of each of the bars. Well, I'll let you work through some of those types of examples, but I don't want anyone to get hung up on the statics, so I encourage everyone to work the statics on these kind of problems ahead of time.